Hello. Today we will be covering Chapter 4, Alkanes and Cycloalkanes. Up until this point, we've done mostly review of concepts that were covered in general chemistry, and today we'll start the first section, which is new information based on organic chemistry. A lot of the different chapters we'll go through, we will work through the different functional groups and learn about them one at a time. And so this is our first functional group, the alkanes. The alkanes are the most simple of functional groups and are hydrocarbons composed of only hydrogen and carbon. There are two general types of alkanes that we're going to be dealing with. The saturated alkanes, saturated referring to the number of hydrogens attached to each carbon. In a saturated alkane, we have the most number of hydrogens possible attached to each carbon. And unsaturated alkanes, which contain a double bond within the structure. So the first thing that we're going to need to look at is learn how to name the molecules. There are two different types of names that we're going to look at with the molecules. The first is just the common names, and historical compounds will often have a common name. This is completely fine to refer to molecules by their common name if you know it, but we'll need a more detailed universal naming system to be able to communicate to each other the different molecules. And this naming system is the IUPAC naming system. There are three main priorities, or that that we'll need to go through when we're naming. The first one is to identify the parent name, and the parent name is going to be based off of the longest carbon chain within the molecule. After we've identified the parent name, we can identify all of the substituents, name the substituents, and add a location to the substituents. So, for example, in this molecule, there are several different places that we could start numbering to identify the parent chain, but we're going to want to find the longest carbon chain within the molecule. So if we start at this position and move all the way to this position is highlighted in red here, we'll find that that's a total of 9 carbons. If we were to include any of these branches, it would be less carbons. So once we've identified the parent chain, there might be, for example, opportunity to have 2 parent chains like this molecule. Here we have 1, 2, 3, 4, 5, 6, 7 carbons. And also, if we started from this place, we would have 7 carbons. So the one that's going to take priority is the parent chain that has the most number of substituents, the most branching possible. So even though they're both 7, the tiebreaker here is that the structure on the left has 3 substituents relative to just 2 substituents. And so here's a table 4.1 from your textbook, which includes the parent name for all of the potential carbon chain lengths up to 15, as well as a few larger ones. You're responsible to memorize the first 10 and to be able to name compounds up to carbon length 10. If the parent chain is a ring, meaning the longest chain length is a ring, then we're going to add cyclo, and we looked at this specific example here in class. But here are a few more examples that will be included on the workbook for you to try. So after we've named the parent chain, our next step will be to name the substituents, and we'll use the same, for the most part, the same naming scheme that we used for the parent chains, but instead of an ane at the end, we have a YL. And so in this molecule, we have our parent chain, and there's 3 substituents highlighted in green. This first substituent is 2 carbons, so it will be an ethyl. This next substituent is 3 carbons, so it will be a propyl. And then finally we have a methyl group. Here are a couple examples where we have both a ring and a chain. And so here, in the substituent highlighted in green, the chain is only 3 carbons, whereas the parent chain is 6 carbons. So the parent ring will take priority, and so we'll have a cyclohexane as the parent name and a propyl group as the substituent. Compare that to this example where now we have the parent chain being a linear chain of 4 carbons, which is more carbons than the cyclopropane of 3. So we have one cyclopropyl butane because of the butane being the longest carbon chain. So for substituents with complex branches, we want to start with the number of carbons that is the longest chain, and then we can start with the carbon attached to the parent chain. We'll name the substituent, and then we'll name and number the substituent side group. So if we look at this example here, a little bit more complicated, it's pretty easy to identify the longest carbon chain. Goes down through here, right? But we have this group here, which is a complex substituent. So we're going to then start the entire naming scheme over for the substituent. We identify the longest carbon chain. Remember, we have to start at the carbon attached to the parent chain, and then identify the substituents within the substituent, which would be a 2-methylbutyl is our total name for this substituent. With common names, there are a few other common names that we have available to us, and these common names are for some of the smaller branched carbon chains. So if we look here, we have a propyl group. Propyl group can also come as an isopropyl group where the parent chain is attached to the middle carbon of the propyl group. So 1-methylethyl would be the IUPAC name for this group, but the common name would be isopropyl, which is completely acceptable to use. With a butyl group, we now have 4 carbons, so there's additional branching possibilities available to us. So we're actually going to have 3 potential branching possibilities. We have sec-butyl, which would be the 1-methylpropyl. Sec-butyl, we have isobutyl. Notice that this carbon now has 2 methyl groups attached to it. And then tert-butyl, where we have 3 methyl groups attached to this carbon. So let's put everything together. To begin with, the carbons in the parent chain, we want to start by numbering them. We want to put the substituent in the lowest position possible. And then we can start numbering them. This would be a methyl in the 2 position. So 2-methylpentane means that we have a methyl group on carbon 2 of a pentane chain. If we have a substituent present, we want to number it so that it's the lowest number. So this parent chain of 7 carbons could be numbered in 2 potential ways. One of them puts a methyl group at carbon number 2, and one of them puts a methyl group at carbon number 6. We're going to want to use the numbering system that puts the methyl group at carbon number 2, giving it the lowest value possible. When we have multiple substituents present, we want to number the parent chain in such a way that gives the first substituent the lowest number possible. So here we have the opportunity to put a methyl at 2 and 2 methyls at 5, or 2 methyls at 3 and a methyl at 6. So the correct way is going to have a number at 2, a substituent at 2, instead of a substituent at 3, because 2 is lower than 3. In this case, there's a tie, right? If we number from the left side, we'll have a substituent at 2, and if we number from the right side, we'll have a substituent at 2. So then we want to look at the next substituent over. This numbering system on here puts a substituent at 3, whereas this numbering system here puts a substituent at 5. Since 3 is lower than 5, the structure on the left would be the correct numbering system. And finally, if there's no tiebreaker based on the placement of the substituents, then we're going to want to look at the substituents themselves and assign based on the lowest number alphabetically. So B comes alphabetically before C, so the numbering system which puts the bromine on carbon 1 would be the highest priority. When we look at our cycloalkanes, we'll hold minimizing the number as the highest priority as well. In this structure we have 1,1-methyl, and in this structure we have 1,3,3-methyl. So we're going to want a number so that we can put both methyl groups on carbon 1. Alright, and to summarize, we'll assemble the complete name, put the number and name of each substituent before the parent chain, and this is in alphabetical order. We ignore these prefixes that we can use if multiple substituents are identical. So for example, if we have 3 methyl groups at the 2, 4, and 6 positions, it would be 2, 4, 6 trimethyl, but we would ignore the tri when we're alphabetizing the substituent, so it would go off of the methyl. So kind of in summary, 1, identify the parent chain. 2, identify and name all of the substituents. Number everything and assign locations to minimize the numbers. And then finally, we'll list the numbered substituents alphabetically before the parent name. Next, we'll move on to naming of bicyclic compounds, which will get a little bit more confusing. A bicyclic compound is going to contain 2 fused rings. So you can see these 2 carbons are shared between 2 different rings, 2 different 5-membered rings. And then also a 6-membered ring, right? There's actually 3 rings in this structure. So this is one point of view of looking at the molecule. Here's a different angle to look at the molecule. The positions that are shared by all 3 rings are called the bridgehead positions, and that's where the fusion between the rings occurs. So from these bridgehead positions, there are 3 potential paths, right? We'll start at this green position here. We could go down and to the left, and there's 2 carbons. We could go down and to the right, and there's 2 carbons, or we could go up and there's 1 carbon. So we want to count the number of carbons in each of these paths. So for example, for this molecule, we said there was 2, 2, and 1, and the total number of carbons is 7, so it's a heptane. So this would be bicyclo-2,2,1-heptane. On this molecule here, if we do the same exercise, if we go down and to the left, we have 1, 2, 3 carbons before we run into the next bridgehead. We have 1 carbon in this direction, or we have 1 carbon in this direction, so it would be bicyclo-3,1,1-heptane. Total of 7 carbons makes it a heptane. Going through the naming, and this is kind of future information. You don't need to memorize this now, but different functional groups have higher priority. So this is just kind of a list and order of the priority of functional groups when it comes to naming. This will be a chart that you might need to reference in the future, but I wouldn't pay too much attention to it now. Just know that you have it here in your Chapter 4 notes if you want to look at the functional group priority relative to naming, as well as the suffix for each functional group. And as we go through the different chapters, we'll learn these one at a time. So we're going to take a look and step all the way back to constitutional isomers, which we talked about in Chapter 1, and talk about them relative to alkanes. So if you can recall, isomers have different structures but the same molecular formula. Constitutional isomers have different connectivity of atoms and the same molecular formula. So as the number of carbons increases, the number of potential constitutional isomers will increase. As the number of carbons in the molecule increases, the amount of different ways that we can put that molecule together becomes much larger. And we can look at table 4.4 here. Molecular formula with 3 carbons has only 1 potential constitutional isomer. If we increase to 4, we go up to 2, 5, 3, and then you could see as we get to like carbon 9, all of a sudden we're at 35 potential ways to put that molecule together. These are all the constitutional isomers that have 6 carbons, so there's 5. But you'll notice we have 2 molecules here in green that are labeled as the same. And so maybe at first glance they don't look exactly the same because of the angles. But if we're able to flip the molecule in 3D space and rotate around its single bonds, at some point it will be superimposable on the other molecule. And that's something that we're going to focus on throughout the rest of the Chapter 4 video, is different ways to view these molecules in 3-dimensional space. So if we look a little bit more at this example, 180-degree rotation around this carbon-3, carbon-4 bond would make it more obvious that they're the same molecule. Another way that we can identify that they're the same molecule is to name them. If we number the parent chains and name these molecules, we'll get the same IUPAC name for the same compound. So different isomers are going to have different relative stabilities, and we can experimentally determine these stabilities by blowing the molecules up and measuring their heats of combustion. So in general, the more branching that a molecule has, so for example, this molecule is much more branched than this kind of linear alkane, then the lower in energy the molecules will be, and the less will have released during combustion. In general, we're going to have a lot of alkanes used in industry, and these are all isolated from petroleum and through oil, crude oil. So the different size of alkane we have are the different fractions of oil. So they're separated by distillation. So we heat the oil up, and as the fraction goes into the gas phase, it can recondense. And so if we look at our carbon 1 through carbon 4 fraction, that's stuff like natural gas and chemicals that are used for plastics. Carbon 5 to carbon 7, used for solvents. Carbon 5 through carbon 12, this is our largest fraction as far as use goes, right? This is our gasoline fraction. And as we get larger fractions, carbon size, there's different uses. Our gasoline fraction of the crude oil only makes up about 19%, but this is the most valuable and sought after fraction. So there are a couple techniques that we can use to convert alkanes to these sizes. Gasoline is a mixture of straight branched and aromatic hydrocarbons. We can use cracking to take fractions that are larger than the gasoline fraction, and this is hydrogen gas, 200 atmospheres pressure, so this is extremely harsh conditions, and 450 degrees Celsius, and we can crack our large alkanes into smaller ones, and we can convert our straight chain alkanes into branch alkanes through reforming. So using these processes, we're able to increase our yield from 47% up to 47% instead of the original 19%. So when we're analyzing the three-dimensional structure of alkanes, there are a few notations that we can use to represent the 3D shape of these compounds. So the wedge and dash is going to indicate, the wedge indicates that this hydrogen is coming toward. So there are several different ways that we can represent these alkanes in 3 dimensions and have a little bit better idea of their spatial arrangement. The first method is to use the wedge and dash notation. So this wedge indicates that the hydrogen is coming towards us, and the dash indicates that that hydrogen is going into the screen, into the plane of the board away from us. The sawhorse method has it kind of elongated carbon bond here. And then finally the Newman projection method, which is gives the most information. In this method, we're actually looking directly down this carbon-carbon bond. So you can't see that carbon bond anymore. But what you can see is this carbon has 3 hydrogens attached. Here are those 3 hydrogens. And then the circle represents the carbon in the back, and those are the 3 hydrogens attached from that. So what this allows us to do is to compare the bond angles between hydrogens attached to the front carbon relative to hydrogens attached to the back carbon. And this is ideal for comparing the relative stability of the possible conformations that occur when we rotate these bonds. So we could rotate this carbon-carbon bond. So we can basically grab these three methyls and rotate them clockwise or counterclockwise while leaving these three hydrogens while leaving the three hydrogens in the back the same. So looking down this carbon, you can see the little eyes looking down the carbon. This will be the front carbon, and then the carbon attached to the blue hydrogens will be the back carbon. So this is a different perspective to look at the molecules. So let's take an example to draw this. Right, start by just drawing the molecule out, looking down this carbon-carbon bond. We can see on this front carbon, we have only a methyl group attached, which means we have two hydrogens attached. So we have the methyl group drawn in with the two hydrogens. In this back carbon, we have a wedged carbon, and so, we have a dashed carbon, which means the one hydrogen attached is going to need to be wedged. And so if we rotate this back carbon, we could see that the methyl group is going into the plane, the chlorine goes up, and then the hydrogen would come towards us or be on the right side of the molecule. And so practicing converting from the line and stick to the Newman conformation is going to take a few repetitions, but one of the things that you could do is use your model kit to kind of confirm your results that you get while you're practicing drawing these Newman projections. Here we have the other conformation at this carbon. So instead of a methyl group that's a wedge, that's a dash, we have a methyl group that's a wedge. So we can practice drawing this Newman projection and compare it to the Newman projection here. So the angle that we have between the two hydrogens in this Newman projection is going to be the dihedral angle, and so it's going to generally be at 60 degrees in this staggered conformation when all of the hydrogens are as far apart as possible. So this molecule is ethane. On both carbons we have three hydrogens. There are basically for ethane there are two potential conformations. There's going to be the staggered conformation, and that's the conformation that we looked at already, that has the 60-degree angle between the hydrogens. Now, if we rotate one of these carbons, so the carbon-carbon bond, right? If we rotate these hydrogens all to the left here, we can enter the eclipsed conformation, and this eclipsed conformation has the two hydrogens very close to each other in space, so we're going to have a negative interaction. There's going to be a torsional strain, which is going to cause an increase in energy. So as we rotate this carbon-carbon bond 60 degrees, right? We start here. We have the two hydrogens that are fully staggered, right? They're as far apart as possible, and the 60-degree angles. If we rotate it, now we have all six hydrogens overlapping with each other. So three pairs of hydrogens overlapping with each other. This costs us 4 kilojoules per overlap, so 12 total, and has an increase in potential energy. So this molecule is not in a happy state because these hydrogens are bumping into each other, and we have torsional strain. Then, if we rotate another 60 degrees, we go back to the staggered conformation, which is low in energy again. You can see our two hydrogens, which were originally across from the molecule, are now next to each other. We could rotate it another 60 degrees, back to a staggered conformation, and we can continue back and forth. So the electron pairs of these two hydrogens are repulsing against each other. They're too close in space, and so each of these interactions, these negative repulsion interactions, costs us 4 kilojoules per mole. Since we're experiencing 3 total, that's a total of 12 kilojoules per mole. So with an energy difference that high, at room temperature, 99% of the molecules are going to be in the staggered conformation, right? This is a happy place. The hydrogens are far apart from each other. We don't have that negative interaction. And only 1% of the molecules will be in this eclipsed conformation. there's another way that we can explain this energy difference between the two conformations. On one carbon hydrogen, so here's ethane again, but we've drawn out some of the orbitals. We have the bonding molecular orbital of the sigma bond between the carbon and hydrogen. And on the staggered orbital, remember in the staggered, we have one hydrogen 180 degrees perpendicular from the other carbon hydrogen. So we're going to have an overlap between the antibonding orbital of the other sigma bond. And this antibonding orbital is empty. There's no electrons in it. And the bonding orbital has electrons in it. So we have an overlap between an empty orbital and a filled orbital. And this has another stabilizing type of interaction that can occur. So let's look at the Newman projection for propane. Propane, now we have a carbon attached. So we have the two carbons that we're looking straight down, and then we have a third carbon attached. Here we have a carbon in the staggered conformation with all the hydrogens. As we rotate 60 degrees, now this carbon is eclipsed with one hydrogen. That's going to actually be worse than the original 4 kilojoules per mole for each interaction, right? We have two interactions of the hydrogens at 4 kilojoules per each. This is 14 total, so this must be 6 kilojoules per mole for this interaction. We can go back to a staggered conformation, back to our happy place. 60 more degrees gives us another eclipsed interaction, and so on. So what is the energy cost of a methyl group hydrogen overlap? Well, a hydrogen-hydrogen overlap was 4 kilojoules per mole, and so our total is going to be 6 kilojoules per mole for the methyl group. Methyl group is going to be larger than a hydrogen, right? Bulkier, so we're going to have a larger energy cost for that overlap. What about butane? Now for butane, we have 4 carbons, and so in this energy diagram we're looking at carbons 2 and 3 of butane. We're looking down the bond of the 2 carbons in the middle of butane. So each carbon is going to have one methyl group attached to it. In this first conformation, we have the fully staggered conformation. This methyl group is as far away from possible as this one. This is the most stable. If we rotate 60 degrees, now we have 3 eclipse interactions, right? We have a hydrogen-hydrogen eclipse. We have a hydrogen-methyl eclipse and another hydrogen-methyl eclipse. This is going to have a total of 16 kilojoules per mole increase in energy. Then we have a dip again. We're going back to a staggered conformation. However, this staggered conformation is a little bit different than we've seen before. We have a gouge interaction between these two methyl groups. That occurs when in a staggered conformation, you have two bulky groups that are directly next to each other. This wasn't an issue with our hydrogens because of how small they are, but these methyl groups are much larger. So we're actually going to have a 3.8 kilojoule interaction here that costs us some stability with this gouge interaction between the two methyls. The highest energy conformation that we're going to have is when the two methyl groups are directly overlapped. We have the two largest groups eclipsed with each other. That's a 19 kilojoules per mole between the two hydrogen interactions eclipses and the methyl group eclipse. Then we have another gouge interaction. We have a conformation that's similar to this conformation. And then finally, we're back to after 360 degrees, we're back to our original staggered. And so we can go through and calculate the energy difference of each of these interactions. So our anti-interaction and methyl groups furthest apart, we decided that was the best interaction. Our gouge interaction, we have the two methyl groups directly next to each other, but still 60 degrees apart. The total energy cost for the highest conformation was 19. We got 8 coming from our hydrogen interactions, so this methyl interaction is costing 11 on its own. So this is a huge cost in interaction. This is a very unhappy state for the molecule to be in. So here are the energy costs for the 4 types of interactions. So if you're given a molecule, you should be able to calculate the energy difference for any state of the molecule. All right, now we're going to change pace a little bit and talk about cycloalkanes. So in the cycloalkanes, remember we have an ideal bond angle for sp3 hybridized carbon of 109.5 degrees. If cycloalkanes were flat, each carbon in the ring would experience angle strain. So only a 5-membered ring is close to this 109.5 degree ideal bond angle, but rings that are smaller or larger are going to have different bond angles than the ideal 109.5, and they'll have some strain involved with that angle. They're going to do anything they can to get closer to the 109.5. Also, if we had a flat ring, then all the carbon-carbon bonds would be eclipsed, and that would cause torsional strain, which we just kind of looked at in the Newman projections. So let's look at the heat of combustions per methyl group for all of these cycloalkanes. So per methyl group, or per methylene group, we could see that it's 700 for 3 carbons, and it goes down until we hit 6 carbons. After we hit 6 carbons, it starts to go up again. So this is some experimental data indicating that the cyclohexane is our most stable ring size because the amount of energy released per methyl group when it's combust is the lowest. And that fits, these are actually all pretty close to each other, the pentane, hexane, and heptane. But there must be something special about the 6-membered ring because look, the bond angle for the 108 degrees on the 5-membered ring, you would expect that to be the lowest, but it's actually this 120 degree with the 6-membered ring that is the lowest. And you can kind of see this data represented in a table. We see that a ring size of 6 is the most stable size of the ring. So why is that? Well, the cycloalkanes all adjust their conformation in space to minimize this torsional strain and the angle strain. So for example, here's cyclobutane. It's far less stable than cyclohexane, and the angle strain, even when it's puckered, right, this puckered conformation that it takes, its angle strain is still going to have 88 degree angles. And we also experience torsional strain. So this molecule is actually a very unhappy molecule. Cyclopropane is a little bit more stable. Some of the torsional strain is minimized. We can compare that to cyclopentane. So it's just a little bit less stable than cyclohexane. Here we have very little angle strain. If we slightly pucker the cyclobutane, we can get the bond angles to nearly 109.5 as it develops this envelope conformation. It reduces both the angle strain and the torsional strain. Cyclohexane is going to be our lowest energy molecule, and that's because it has the ability to do the chair conformation. So if we look at the different potential ways we could draw a 6-membered ring in 3D space, we have the chair, half chair, twist, boat. The chair is extremely low in energy compared to the rest of these. And that's because in the chair conformation, we're going to be able to obtain 109.5 degree bond angles, so we have no angle strain. All of our bond angles are 109.5 degrees. And if we look down these bonds, right? This is a double Newman projection. We're looking down this bond on the top arrow here and this bond on the bottom arrow here. We could see that all of the hydrogens and all of the carbons are in the staggered conformation, so we have no torsional strain. So between these two factors are why the chair cyclohexane is the most stable conformation for a ring. Now, this is going to be one of the tricky parts, is learning to draw the chair conformations. And the best tip I can give you is that all of the lines are parallel sets of lines. So you could start, you draw a V, and then you can draw a line going down at a 60 degree angle, ending just before the center of the V. Then we're going to start drawing our parallel lines. So this fourth line is parallel to this line is parallel to this line, and then this line is going to be parallel to this line. And so you're basically drawing out 3 sets of parallel lines, and the best advice I can give you is to just practice. Draw as many of these as you can, because we'll be using cyclohexane a lot throughout the course, so you need to be able to draw the 2 different chair conformations, right? You can kind of compare the molecules here on top to the molecules on bottom. They're just flipped from the different sides. So if drawn correctly, the chairs should contain 3 sets of parallel lines, and they're highlighted here in red. Now each substituent on the ring, right? So each of these is a methylene group. It's going to have 2 substituents. Has the possibility of being either axial or equatorial. And so this is an important distinction because these are going to be separate positions. Now the axial position are always going to be the lines that are going either straight up or straight down. And the equatorial position will always be coming out at an angle. So we can look at multiple of these positions. Adding the axial positions is easy. They always point straight up or straight down and alternate around the ring. So here's a ring with all 6 axial positions drawn in. You can see if the angle of points downward, then the axial goes downward. If the angle of the 2 carbons together points upward, then the axial position goes upward. And you alternate around the ring, up and down, for the different axial positions. So here we have 2 carbons, 2 bonds that meet pointing downward, so the axial goes downward. And then the equatorial position is going to be parallel lines for each molecule. So they're going to run, so for this 2 bonds here highlighted in red, the 2 carbons in the middle of them are parallel lines to those 2 carbons. Here we have the 2 parallel carbons in red, and the equatorial position for the 2 carbons attached in the middle of them are parallel lines. So you can see after we finish drawing in all of the substituents on the molecule, we have in highlighted red all of the axial positions, and then highlighted in blue, we have all the equatorial positions, which are all parallel to the carbon bond 2 carbons over. Each cyclohexane has the potential to have 2 conformations, and the conformations allow from a substituent to go from an axial position to an equatorial position. And this occurs with the ring flip. So you can envision taking your finger, pinching this carbon, and pulling it upwards, and pinching this carbon and pulling it downwards. And that is a ring flip. This is definitely something that you're going to want to practice doing with your model, but you could see something in the axial position after a ring flip is going to move it to an equatorial position. If we look at our double Newman projection, we could see the rotations that occur, and we could see that the substituent in the equatorial position moves to an axial position. If we look at methyl cyclohexane, we're going to have the 2 chair conformations possible, and we would observe that 95% of the molecules are in the chair conformation with the methyl group on the equatorial position. So the equatorial position is going to be more stable than the substituent in the axial position, and this will be about a 95% ratio. The biggest reason that this occurs is because once a substituent is in the axial position, there's going to be steric interactions that destabilize the conformation. So if we look at the gauge interaction, right? Remember the gauge interaction of having 2 methyl groups next to each other. And we look at the chair conformation with the double Newman projection of a methyl group in the axial position. One of these gauge interactions is occurring with the methylene group on the adjacent carbon. So if we have a 1,3 diaxial interaction, or the interaction that's occurring between this methylene and the methyl group, that's going to be similar to a gauge interaction. And if we have the methyl in the equatorial position here, you can see it's pointed away from, it's staggered with the methylene group, and so this is a very important way to minimize the amount of energy that's present there. So in general, each atom or functional group or set of atoms is going to have a different tax for these 1,3 diaxial interactions. A chlorine is fairly small, so it's only going to cost 2 kilojoules per mole to be in the axial position. And alcohol is a little bit larger. That'll cost 4 kilojoules per mole. And as you can see, once we get to methyl, that's where things really start to affect the equilibrium. We're charged 7.6 kilojoules per mole, and 95% of the molecules will put the methyl group into the equatorial position to minimize this energy. If we look at a tert-butyl group, which is a huge bulky group, we have almost 10,000 to 1 ratio. So as we practice more, drawing out more of these molecules, we could take chlorine attached going with a wedged line and a methyl attached with a dashed line, and convert them to the chair conformation. And we'll do a bunch of practice with these on the worksheet, but you could see these are on opposite sides of the molecule. So the chlorine is going up in the axial position and the methyl is going down in the axial position. When we do a chair flip, they both go from axial to equatorial, and this is the lower energy conformation. When we want to name these compounds, we now have another piece of information that we have to include, which is the relationship between these two molecules, between these two substituents. Are they on the same side of the cyclohexane face, or are they on opposite sides? So if they're on the same side, we refer to them as cis. So this will be a cis 1,2 dimethyl cyclohexane. And when it's on opposite sides, we can refer to them as trans 1,2 dimethyl cyclohexane. These are going to be referred to as stereoisomers, since they have the same atom-to-atom connectivity, but they have a different spatial arrangement. And we can look at the two energy conformations of these. So we have the two chair conformations. These methyls are on the same side, so we have one that's axial, one that's equatorial, and when we do a ring flip, the equatorial one converts to axial and the axial converts to equatorial. So these two chair conformations have the same amount of energy. Whereas when we have a trans relationship, we're going to have the two methyl groups both as axial or both in equatorial. And the lowest energy conformation would definitely be when they're both equatorial. So our final slide is polycyclic systems. So a decalin is when we have two six-membered ring fused together, and we need to look at the relationship between the hydrogens attached at these positions. So this would be a cis decalin, comparing the two hydrogens are on the same side of the molecule, whereas a trans decalin we have axial relationship of both of these hydrogens, one on the top face of the molecule, one on the bottom face of the molecule.